Good morning. I'm Stephanie, and our topic for discussion is application of engineered yeast biosensors mycotoxin detection. So mycotoxin mycotoxins are secondary metabolites produced by various toxigenic fungi belonging to Aspergillus, Ethereum, and Penicillium. The mycotoxins are fungi. So our presentation is going to be about examples of mycotoxins, problems, detection, advantages, and disadvantages. So examples of mycotoxins, we have aflatoxins, which can be found in corn, peanuts. So we have an illustration of corn and peanuts infected with mycotoxins. We have coffee, and there is grape, which are dried fruit infected with mycotoxins. So these and many others. We also have John and Zearalenone in maize. These are mycotoxins which are contaminated food. So we are going to talk about our problem. So existing mycotoxin detection methods are expensive. Some require specialized equipment and often need trained personnel to operate. So there was a time in Kenya in 2004. Kenya was an outbreak of aflatoxin, which is from aflatoxin, which is a mycotoxin, and there was also one which happened in Benin, which was caused by first women. First women is within the period of 4 to 6 months where a child was infected. That means the food, they couldn't detect the mycotoxin in the food given to the child, therefore leading to impaired childhood. Therefore, there is an urgent need for cheaper mycotoxin detection methods. Thank you.
Good morning. So talking about the current detection methods, we have the high performance liquid chromatography. The high performance liquid chromatography, as it is not accessible to the low income clinics and also not effective because it is time consuming. A lot of we are looking for a method that is very accessible to low income clinics. So that's a problem from the high performance liquid chromatography. We also have the ELISA, enzyme linked immunoabsorbent assay, which require biosensors and specialized equipment. These specialized equipment are quite expensive and are not accessible to the low budget clinic. We have the liquid chromatography, tandem mass spectrometry, which is complicated. It's a complicated sample preparation protocol. It's not easy and it requires large expertise, which a lot of biology do not have. So our proposed detection method, we plan on using the yeast engineered yeast strain mycotoxin detection in food. So for our requirements, we will need plasmid detector, promoter genes, reporter genes, and stability genes. Our molecular biology reagents will need the reaction enzymes, ligase, and PCR reagents. These reagents are easily accessible. For our transformer reagents, we need lithium acetate PEG. For our selective media, we need SD-ORA for plasmid selection, and detection equipment, we need fluorescence microscope or beta-galactose assay kits.
I'm Maxwell, and I'm going to talk on the protocol. So step 1, we are going to design our plasmid constructs. We are going to identify promoter sequences, obtain mycotoxin responsive promoters, select reporter genes. The second one is cloning the promoter, reporter, and stability genes, where first we are going to do amplification using PCR, restriction digest, where we are going to use restriction enzymes, and ligation, we are going to use the ligase enzymes. Step 3, we are going to do transformation into Saccharomyces cerevisiae, where we are going to grow our yeast to maximum, where they grow to maximum growth, mix plasmid DNA with yeast, and then incubate with lithium acetate, where we are going to design so that our promoter genes are going to be upstream of reporter genes. Step 4 is selection of transformants, where we are going to grow on the SDURA media, our yeast cells. The transformed yeast cells are spread on the media, incubate at 30 degrees for 2 to 3 days. Step 5 is confirmation of successful transformation, where we are going to use colony PCR, confirm presence of inserted genes, and also sequencing to verify correct insertions. Next, we have functional testing of the engineered yeast. We are going to do induction with mycotoxins, expose modified yeast to food samples with mycotoxins, where we are going now for detection. We are going to either use fluorescence assay, observe the green fluorescent protein under fluorescence microscope, or calorimetric assay, where we are going to perform beta-galactosidase assay for LAC-Z. The very last one is stability and longevity testing, where this year we are going to measure on stability genes to ensure that our Saccharomyces cerevisiae is effective and efficient for detection. This is basically what I've been describing. It's an illustration. Advantages, we have low cost compared to current methods, easier to use, requiring minimal training. It is scalable for both small and large operations, potential for detecting multiple mycotoxins with one test. And some of the disadvantages, since it cannot be perfect, may have lower sensitivity compared to some current methods, potential regulatory hurdles for using genetically modified organisms, and possible limitations in quantitative analysis. In conclusion, our method is cheap and cost-effective, so it's the method as compared to other current methods. This is the way methods, since it adjusts to the principles of physical science. Thank you. Fragile science. Thank you.
Thank you.
Thank you.